Chapter 10, Navier-Stokes Equation. Okay, everyone, today let's imagine that fluid is like a group of tiny invisible marbles all trying to move around. These marbles bump into each other, sometimes they go fast, sometimes slow, and sometimes they get stuck to walls. Now, engineers love to predict how these marbles move, especially when they are inside pipes, around airplanes, or in rivers. To understand this, we use something very famous called the Navier-Stokes equation. You can think of it like a super rule book that tells the fluid marbles how they should move and behave in every situation. But this rule book is very long and very hard to solve, like a huge math puzzle that only the world's best computers can solve fully. So, what do engineers do? We try to make it easier by using clever shortcuts called approximations. One shortcut is when the fluid moves really slowly, like honey dripping from the spoon. In this case, it's called creeping flow. Imagine pushing a spoon into a jar of thick honey. You have to push really hard because honey resists moving, and the fast-moving effect is gone. In creeping flow, we say the sticky force called viscosity is the boss, and the speeding up or inertia becomes so tiny that we don't care about it. So the equation becomes simpler, and we can easily count how much force is needed to move something in honey. Then we have a second shortcut when the fluid moves really fast, like wind hitting a car. Here we can ignore the stickiness far away from walls because the speeding up of the fluid is more important. This is called Inviscid flow. It's like when you're biking and you feel the wind push on you hard, but the air stickiness is too weak to matter far from your skin. But near the car surface, we can't ignore the stickiness, so we have to be smart and only use this trick where it makes sense. Another fun shortcut is called irrotational flow. Imagine you have no spinning in your fluid. Everything moves straight and neat. Like a peaceful river far away from rocks or walls, the flow doesn't swirl or twist. In this case, we use something called the velocity potential, which is like giving every point in the fluid a number that tells us where it wants to go, making our calculations much easier. Sometimes we mix these tricks. For example, in an airplane, most of the air around the wings can be thought of as inviscid and irrotational, but right next to the wing, we have a very thin sticky layer called the boundary layer. In the boundary layer, the fluid slows down because it sticks to the wing. Outside this layer, the flow moves quickly without caring about viscosity. We also use smart numbers like the Reynolds number, which tells us if the flow is more sticky or more speedy. If the Reynolds number is really small, we use creeping flow. If it's really big, we can ignore stickiness far away from walls. Finally, when we can't solve the full big equation, we don't just give up. We use these tricks to make the math easier so we can design airplanes, cars, ships, and pipelines safely without waiting years for a computer answer. It's like playing with Lego blocks. You don't have to use all the pieces, just the important ones to finish your design. That's how we make the Navier-Stokes equation more friendly for engineers.